Welcome everyone to the Machine Learning Red Hat Process Automation Manager, formerly known as BPM Suite, and Reactive Microservices session. I'm Andy Bonham, Principal Software Engineer from Capital One.
Hi, I'm Murph, Solutions Architect at Red Hat.
Hi, I'm Rishi Menon, a Lead Software Engineer with Capital One.
So a couple quick facts about Capital One. We're a leading diversified bank. We have major operations in the U.S., in 15 different cities. We have an office actually right next door to the South Building. Also New York City, Plano, Texas, Chicago. McLean is our headquarters in Virginia, and also Richmond. We have about 70 million customers and around 49,000 associates. And we've been honored to win several awards from the Fortune 500 list. In terms of where we are with some of the other banks in size, you can see there 6 in total loans at the end of 2017 and 8th in U.S. deposits. And we've been on a journey since the company was founded about 25 years ago, where we initially started off as a credit card company and then started to diversify ourselves into a bank. And then more recently, probably in the last five or 8 years, we've been transforming into a tech company that produces banking products. So we have a dev exchange out there, Capital One Dev Exchange, you can go to and see some of the open source products that we've produced. Hygia is one you may have heard of. It's a DevOps dashboard. Cloud Custodian is another one that is a rules engine that allows you to manage your AWS services, along with several others. And then on the Dev Exchange, there's some technical blogs from our experts and webinars that you can take a look at. So at Summit last year, we presented a similar topic. Did anyone attended that session last year? Okay. So last year, we showed how you can use BPM Suite, reactive microservices, with an emphasis on how you can deploy those using Docker and a container management solution, specifically ECS, Amazon's ECS. And the use case, where we kind of started on this work was a use case where we were doing different prototypes for a future state of our decisioning platform. And we wanted to show how we needed a solution that would allow us to coordinate a pretty complex series of workflow over a number of dimensions, but also integrate some of the latest patterns with microservices and decoupling the different components together, because we wanted to avoid that coupling. So that was the session last year. The session this year, we're going to extend upon that proof of concept that we built and show how you can use that same pattern to integrate machine learning. So we'll focus less on the container management approach and more on the machine learning piece. Now I'm going to hand it over to Rishi, who's going to talk about some microservice and reactive architecture concepts.
All right. Thanks, Andy. You guys can hear me okay? All right. Hope you guys are having a great conference. So my agenda, I'm going to talk about advantages of microservices over monolith application and comparison between two architectures that we're going to take a look today, that is orchestration versus reactive architecture. And I might focus a little bit more on reactive architecture because that's what today's demo is going to be all about, right? Use BPM and machine learning along with reactive architecture. All right, so moving forward. And we are well aware that we might be the only guy standing between you and lunch, so we'll try to make it fast. All right. Do you guys like the picture out there? This is how a monolithic application looks like. An electrician would be really scared to even touch it, right? So let's start off with the definition. Typically, a monolithic application is a single-tiered application which has both the user interface code as well as the data access code combined together to form one big software application, right? You remember the days when we used to deploy like a 200 MB WAR file, like until 5 years back. I mean, some of us even do it today because, if it's an end-of-life application, why to invest more? But yeah, it used to work fine in a non-cloud, non-digital world. when the business requirements were not quick and not evolving fast, but the disadvantages of monolithic applications started showing up gradually, right? So there are many disadvantages of monolithic application, but let's focus on the big ones today, right? So number one, no fault isolation. So suppose your application or your monolithic application has the code for n number of business functionalities, and if one of them fails, you have to repackage and reassemble the entire application, right? So the entire application is impacted. That's what I mean by no fault isolation. Then we have reduced agility. This also means reduced agility because it takes more time, again, to repackage the application and deploy it into production. And Agile is all about incrementally delivering value as early as possible, right? Suboptimum scalability or suboptimum resource utilization. For example, if you, again, consider a monolithic application which has n number of business functionalities, right? So I'm from a bank, so I would say customer login, payments, rewards. And if we figure out that the login functionality needs more resources, the way how we used to scale it out is deploy multiple instances of the monolith application. And what we end up doing was reserving, like indirectly reserving more resources to the functionalities which never needed it. And that will be like resource wastage, right? And the last but not the least, it was definitely not DevOps friendly. Again, when we get CI/CD into the picture, it used to take forever to, again, repackage the application, and it definitely decreased the frequency of the production deployments, right? Moving on, say hello to microservices. So microservices have been around since 2008, but it became famous. The term was coined, I think, in 2011, and it became really, really famous after once Netflix entered this microservices area, right? Advantages of microservices, there are a lot of advantages, but let's focus on the top few. Fault isolation or fault tolerance, right? If any of the service fails, we can independently fix it and deploy it. And the other components or the other services are not impacted. Number two, small. The code base is going to be really small, so it's going to be really easy and fast for the developers to understand the code base and make fixes and deploy it, right? Polyglot. As a big monolith is broken down into n number of microservices, they can be written in different programming languages. You don't have to stick to the same language. For example, one can be written in Java, other can be written in Go. In fact, I've also seen some enterprises going for polyglot persistence, where they have used multiple databases. And optimum scalability, that's one of the biggest advantages. So if you figure out that only one service needs more resources, you can horizontally scale it out to n number of instances and keep the other services as is. Moving on. Extending on the concept of microservices, we are going to talk about, so these are the two architectures, high level, we are going to talk about today, like orchestrator versus event stream. Now, orchestrators versus reactive architecture. So whatever you see on the right-hand side, that's reactive architecture. That's basically a concept of microservices applied to event-driven architecture, right? So let me give one-liners about each keywords. So event means something significant has happened in the domain, and it is immutable. For example, if a customer logs in, that's an event, and that event can be published by one application. It can be consumed by anybody else who is interested. This event stream can be a dump message pipe, dump message bus like Kafka. And with that, I don't mean to say that Kafka is dump. What I mean to say is that event stream should not have any business logic, right? So that's in reactive architecture, and you can, looking at the figure, you can easily figure out that there is parallel processing going on. Service number A can consume some events or messages from the message bus, do its processing, put it back there, which can be consumed by multiple services, B and C. So there is a lot of parallel and asynchronous processes going on. Going back to orchestrator architecture, this is what we are more familiar with, and we have been more comfortable with, and we have been doing it for a while. Here what happens is the orchestrator here calls service A first, then it calls service B, then it calls service C. So this is good too, but as long as there is no blocking, right? If we have to wait for like 5 seconds for service A to respond, then wait for another 5 seconds for service B to respond. So that's when it becomes a bottleneck. Again, there are good use cases, so we have to focus on the use cases. There are good use cases for both the scenario, right? For example, if you really want to have the entire process flow in one central place, and if you discover or if you see that your operations cannot be done in parallel, that's when you go for orchestrator service. Versus reactive architecture, if you find out that some or most of your processes can be done in parallel, and it is okay to break down the process flow into multiple services, that's when you go for event stream. All right, moving on. So in 2013, the Reactive Manifesto was born. Basically, this was multiple organizations from different domains coming together to identify a pattern to build better software that would meet the modern requirements, right? So this is what they came up with: responsive, resilient, message-driven, and elastic. Responsive is the main value coming out of it, which means that the application should be responsive and it should not hang, and it should be consistently responsive at the same rate. Message-driven is the means. Using message-driven architecture, you can make it happen. And elastic and resilient, these are the two forms. You know, elastic means as the load increases, the application should be able to scale out and serve the traffic. And resilient means whenever there is a failure, let's say infrastructure failure or failure within the application itself, the application should be able to recover and keep going, right? Okay, moving on. Reactive architecture, if you remember the diagram in a couple of slides back, the two things which stand out is it enables faster end-to-end processing because parallel and asynchronous processing is happening. And there is no central point of failure because, as you remember, there are multiple services, right, doing their job and publishing the messages onto the event stream. So there is no single point of failure. If there is something wrong with service B, that can be fixed independently by not impacting the other applications. And the services are completely decoupled, which also means that it supports experimentation. Suppose you want to try out some experimentation by adding new functionalities in, let's say, service A. You can do that, see how it behaves, and if it doesn't work, you can take it out without impacting the other applications. And again, reactive architecture can be combined with some other patterns like CQRS and event sourcing to have better outputs. Yep, so Murph will take it forward from here. Murph.
Sure. Thanks. So we talked about some of the concepts that go into the architecture here. Let's talk a little bit about the technology. Even in a microservices world, whether you're going for an orchestrated process using a workflow engine or you're doing a more distributed reactive process, there's still going to be human workflow. There's going to be process structure that you're going to want to be able to surface to your business users as well as to your developers. And Red Hat's Process Automation Manager, formerly known as BPM Suite, includes the capabilities that you need for that. The key thing about it, though, is that it's easily decomposable. All the components, so these are all the things that you can have. Your business runtime, your process runtime, monitoring, authoring, all of those pieces come apart. And rather than dealing with a monolithic process automation system, you're able to have a micro process automation system, or in our case, a reactive process automation system. We want to tie into the event stream that are coming from these other services and publish our own events, react to those events as an active process. So For this demonstration, the event stream is Kafka. So this is our event broker. Out of the box, Process Automation Manager does not have direct integration with Kafka, but what it does have is a highly extensible architecture, and we're able to add these capabilities in. So out of the box, the key server, which is your runtime environment for your processes, already has all of its capabilities defined as extensions. The rules runtime, the process runtime, monitoring, all of that is built in as separate extensions. So we're going to add one more, a Kafka extension, that will allow the runtime to interact with the event stream. So this is a high-level sort of logical architecture for what that breaks down into. The extension itself is responsible for handling create and dispose events for your containers. The unit of deployment in Process Automation Manager is the kjar. It contains your process definitions, domain logic, whatever is necessary for the execution of the process itself. And we'll see an example process in just a few minutes here. When that kjar is created and inserted into the runtime, we want to have our system register the topics that process is interested in. Using some metadata defined in there, we're able to assign the list of topics that we're going to listen on. Then we begin a polling process against the Kafka endpoint, and each of those records can be handed off to a record handler, which are then handed back into the process instance as a signal. So the construct within the process, we're essentially mapping signal events within the process definition to messages coming off of the Kafka bus. There are two other pieces that are needed, so that's for the listening and responding part. We want our processes to react to the events. This is how we accomplish that, by tying those together. But we also want our processes to publish events and participate in the event stream in their own right. There's two ways to do that. One is through a work item handler. This is a tried and true component of the process execution system. You can define any work item handler for any sort of integration with external systems, complex business logic, and insert that as a node within your process description. In our case, we've written one that just publishes things to a Kafka topic. It takes three inputs, the topic, the key, and the value that you're going to write to, and it handles the communication and the relationship with the event bus. The newer thing is the Kafka emitter. Part of Process Automation 7's architecture, so one of the updates that's in 7 is a new API around this event emitter API. Previously, all of your audit information, all of your runtime data as the process engine clicked along would be written out to database tables, these audit tables within your database. We wanted to abstract that away so that you could then replace that. So still by default, we're writing everything to the database, but now you have this emitter abstraction that allows you to publish those events somewhere else. So anytime a process is updated, anytime a process completes, starts, process variables are changed, those can be written out as events to a Kafka topic. And that's what the Kafka emitter does here. So if there are, whether you're using that as a sink that will then write out to Elasticsearch backend, and you want to do some monitoring and management that way, or if you want other business processes or other microservices to react to those process events, you can do that. So you can either be explicit with your business events with the work item handler, or more generic with all of the process engine events with the emitter, or both. So that's the technology behind it. Andy's going to actually take you through the use case around machine learning integration.
Thanks, Murph. Alrighty. So artificial intelligence has been around for a while. Came out in the 1950s, and some of the first systems were known as expert systems, which were built using if-then type logic. And with those, basically, a person had to program that into the system. And then in the 1980s, machine learning started to come around. Has anyone seen the movie Short Circuit? Johnny Five? So yeah, there's a clip in there, right, where he takes, I think it's the English dictionary, and in a matter of 30 seconds, now understands the entire English vocabulary. So kind of an early version of machine learning there. But the idea is that the software algorithms can learn themselves, right? You give them the data, and they can then figure out what are the best things that can predict the target that you're trying to predict. And some of the common things you'll see in there are things like neural networks and different algorithms. Then more recently, deep learning. You can see right outside on the street some examples here with self-driving cars and image recognition. These are algorithms that try to, or that mimic kind of the sensory in the human brain. So really exciting stuff, and things are very quickly continuing to evolve. They're going to change a lot of things that we do in day-to-day basis. From a high-level classification, there's two high-level kind of classifications. There's supervised machine learning and unsupervised machine learning. With supervised machine learning, you basically label your data. And what you do is you provide kind of historical data that has a target. And the target attribute is the thing you're trying to predict. So the idea is you want to provide as much data as you can, so when the algorithm is running, it can figure out what are the things that are the highest predictors to predict the target. Unsupervised is a little different, where you don't provide a target value. Rather, the algorithm itself will figure that out. And it usually does it by clustering, where it'll start and group data that it identifies as being similar in different categories, and then runs algorithms that way. The POC we're going to show to you today is going to use the supervised classification. So what we did is we leveraged H20, which is an open source Apache-based machine learning platform. And you can see some stats here on it. It was written in Java, created in 2011. You can use it with Python, R, a bunch of other languages there, Scala as well. And it gives you a host of different algorithms you can use. Distributed random forest, gradient boosting machine, some of the other deep learning algorithms. It supports both supervised and unsupervised. In this case, we used supervised. And what's really cool is when you build your model, it gives you the option to deploy your model as a Java Pojo. So it'll actually generate the Java code. You could also use a Mojo. Now this isn't the Austin Powers Mojo. This is a model object optimized format, which is it's basically a binary format, and you would use that when you hit kind of size constraints in your Pojo. So if it hits, I think it's a limit of 1 gig from a Pojo, you would use a Mojo, and it's faster from that perspective. So some of the algorithms and the models you build can have a very high number of trees, and that ends up producing a larger model. So as we thought about this, we were thinking there's at least two different options of how you can integrate this with Process Automation Manager. You could take the deployed model or the produced model and integrate it into a microservice that's connected to your event stream, or you could embed it directly into Process Automation Manager as a work item handler. In this example we're going to show you today, we did the first option of embedding it in a microservice that was connected to Kafka. And as we thought about this, we think this pattern can have a lot of value, because one of the reasons a lot of companies will use Process Automation Manager is for human workflow. And if you can build a machine learning model that maybe runs upstream and reduces some of that human workflow, that can translate into cost and other benefit savings. But at the same time, maybe there's things where the machine learning model can be used as part of that task, as those tasks are worked, where maybe it supplements, provides folks additional information to make better decisions. Where maybe when they're working the task, they call an API that calls a model and then helps them, either makes decisions for them, or either can provide some recommendations. So I think there's a lot of potential with that type of pattern. So moving on to our demo, and a couple quick things we're going to highlight here before we actually do walk through it. So this is the example of our business process. And you heard Murph talk about signal events, and that's what the triangle notation icons are. Those are where BPM is listening for a signal of that particular value. And the key server extension that Murph built that's listening to Kafka, it basically parses the events that we're placing on Kafka and passes that back into BPM. So we have an attribute called an action that basically has the event name, and that gets passed back. And BPM interprets it and figures out, if it's an event it needs to react to or not. Next, there's the Kafka service task, and I'll show you that. That again, that's the part of the work item handler that Murph built. It will produce to Kafka. And so in this case, we're basically submitting a command, BPM submitting a command saying, hey, go calculate my features. Then it waits, and we have the calc features microservice that will read that command from Kafka, produce the features. Features are the inputs to the model. That gets published back to Kafka. Then there's a second microservice that reacts to that event and sees the features were calculated and says, okay, I'm going to go and run the model now using those features. Then it publishes back to Kafka and says, okay, this transaction's either okay or it was potentially fraud. And then BPM, if everything's okay, it ends. If it sees the model is identifying as a fraudulent transaction, we'll just write back out to Kafka one more time. And in this case, we just say request fraud evaluation, but you could extend this to be whatever you think the next steps should be. And then to kick off the process, to simulate that, we just created a simple business process that writes to Kafka with the event transaction received. So that would simulate the transactions coming in. In terms of the POC, so we used a data set off of Kaggle.com. There's a credit card fraud detection data set that a UK company put out there, and they anonymized 28 numerical features. So you don't know what they are, but you know that they're numbers. They did provide the amount of a transaction and the time from the first transaction. And then you see the attribute on the far end here, class, that's your target. So it's 1 if it's fraudulent, 0 if it's not fraudulent. So when we run the H2O to build the model, that's what it's going to check and try to figure out out of these attributes, how can it predict that class variable. To build the model, we use H20 Flow, which is a UI that comes as part of H2O. It's really easy to use and get started. You just issue the Java jar command there. Once you're in there, you basically import your data set. In this case, our data set wasn't very large, so we just did it locally on the machine. In here is where you select your different algorithms. And one important thing is you select your training data set and your validation data set. You always want to make sure those two are different, because if you had some data sets get into your training data set, you can have what's called leakage, where the performance of your model could actually look better than what it really is, because you're validating it with the same things you train the model on. So you always want to validate the model on different data than what you trained it with. The other key thing in here, these are the kind of H2O generated variables. The response column, you can't see it here, but it's further down. That's your target. That's the column you're trying to predict. So that's how H2O knows what it's trying to figure out. In our particular run, we ran through at least 2 different algorithms. We started with the gradient boosting machine, generated the POJO, deployed it in our microservice. But as we looked at, these are metrics that H2O provides. The first one, the log loss, you want that as close to 0 as possible. That helps kind of show you the performance of the model. You can see with GBM, it actually went the other way, so we didn't want to use that one. With distributed random forest, we had a better curve there. And then The ROC curve is the receiver operating characteristic, but basically it shows you your true positive rate and your false positive rate. And you can see here the initial model was right around 67% with 0 false positives, and distributed random forest was closer to 88. So a little better rate there and a better curve. So the current POC on GitHub uses the distributed random forest. But one thing, when we switch these out, it was fairly easy. You just import the Java file into your project, redirect the microservice to point to the Java code that you want it to. So that's kind of the nice thing of having it as a microservice. You can just change that one part, deploy a new version, move on from there. The other thing with H2O is it figures out which of the variables or features are the most important. So in this particular data set, you can see the ones up here were identified as being more important to predicting the target. We deployed it as a POJO. There's some steps here if you wanted to run it kind of standalone. So we deployed the POJO and integrated it into an existing microservice that was producing and consuming from Kafka. And now we will switch over to a live demo. All right, so we're running two EC2 instances. One is running a Docker container of BPM Suite. I think in this example we're using 6.3. And then we have another EC2 instance running Kafka, Zookeeper, and our 2 microservices. And so we go over to those real quick. We can see the Docker containers. So this is our BPM Suite Docker container that's up and running. And if we do the same thing on the Kafka instance, we can see there's our 4 Docker containers running there. So what I'm going to do here is I'm actually going to start a Kafka consumer through the console. And this is going to pull up a bunch of data. So this is kind of the stuff we've been testing. But I'm going to clear this out. As the different services are writing to Kafka, you'll see it pop up here. So if we log into BPM Suite, we can take a look at the business process. And this is the same one that we walked through on the slide. Just to show you real quick, the service task, which is the work item handler that Murph built, it's pretty cool. It's just Kafka. You just drag it over. And then over here, you basically tell it the topic you want to write to, the value of the data, and then the key. So Kafka has a key that this implementation is using a key and a process ID for it to integrate. So I've already built this. So if I go to the deployments, what I'm going to do is start that kickoff process. And we should immediately start and see some of the events get posted into our Kafka consumer right here. So we'll start this. Over here, there we go. So we see this initial event here was written by the kickoff business process, transaction received. BPM started its flow and then submitted a command to Kafka that said calc features. The calc features microservice saw that command, calculated some features, populated it back, and then the run model microservice read in those features from the event. It ran the H2O model. You can see here the output. So it gives you a p-dot label, which is that target. In this case, it's 1, which means it's fraudulent. It also gives you a probability on its kind of assessment of the accuracy. And then that last step is where BPM read in the fraudulent transaction event and wrote back out to Kafka to say evaluate fraud. And if we go over here to our REST API, we should be able to see the path that it took. So that's our kickoff process. And then, okay. Try that one more time. Numbers may have gotten, there we go. So we can see in this example, the path that is fully grayed out is the top. This one still has another step, so it confirms what we saw in the log, that it was identified as a fraudulent transaction. And in here, we actually randomized some stuff in terms of the generation. So you can play around with it and submit it a couple times, and you'll get some records that, so in this one, I think this one came back okay. So in the one microservice, there's kind of just 2 pre-baked records that we took from the data set that we know would either be fraudulent or not fraudulent, and it just kind of randomly returns between those. But you could break this down. You know, if some of these features were really big to calculate, you could, if you wanted to, break those into their own microservice if you needed to scale them differently. You know, it all kind of depends on the use case. So flipping back over to our some of the lessons learned with this approach. You know, in this case, we are using BPM as a coordinator. And in kind of a pure reactive approach, you want to you know, eliminate or reduce coordination as much as possible. But in some cases, if you have a really complex workflow that has a bunch of trees and nodes, that it's easier to build the workflow in a model than code, is where we found this pattern valuable. And one of the ways you can you know, reduce the risk of the coordinator going down is just make it as resilient as possible. Correlation IDs help you kind of string the different microservices together in terms of going back and looking at it from an audit perspective. From machine learning, one thing, you know, when you build the model, you want to make sure you use as much data as you can, so that algorithm can really figure out what's the best way to predict that target variable. And then, you know, the model will only be as good as the data, right? So you want to make sure your data is not biased. Otherwise, you'll end up with a biased model. So it's very, very important that the data is good. And then, you know, chaos testing can help. You know, as you have more pieces, you could use chaos testing tools to make sure your resiliency is where you want it to be. And then here's the GitHub repo if you guys want to check it out, and some Dev Exchange blogs out there.